Okay, so second section, we have more, we're gonna learn more probabilities using some experiments and modeling. Okay, so we have multi-stage experiments. It will take some time, but it's gonna be fun. So I'm giving you one example here. So we will consider two-stage experiment here, okay? A ball will be drawn from this box. You see the box there? And I have three different colors of a ball: red, white, and green. Okay? So there are three balls, each different color. The ball is drawn first, then I'm going to replace it. I'm going to put it back. So second draw, there are still three balls, right? So it doesn't affect anything. So think about what's the possible outcomes when I draw balls twice. So take the ball first, okay, and think about what color it will be. And I put it back and think about the second ball. Can you get? Okay, so list all the possible outcomes for that experiment that we're gonna do. So we are drawing ball first from this box. This is what the color could be. It can be red, it can be white, it can be green. And then I flip back. Whether it is red, white, or green, I flip back. So the second ball draw, I still have red, white, and green, right? So you might have, guessed what the outcomes are. You can use, different models. One way, this is just one way, you can make a table like this. This table shows first draw here. First draw, it can be red, white, or green. My second draw can be also red, white, and green because I replaced the ball back, right? Then think about how you can fill these empty cells in. This one will show first row red and second row red. You can maybe put red and red, right? How about this one? Second row is red, first row is red, second is white, so red, white. This one will show first row is red and second row is green, and so on and so on and so on. So can you fill up this table in your notebook? How many of you are done? Okay, okay. Madison? Okay, can you fill up this table for me? Just say out loud. RW, RG, WR, WW, WG, GR, GG. Very good, right? I'm pretty sure you guys have that too. If I say it's GW, what does that mean? Green, white. So first row was green color and the second row was white, right? So we have this table. I'm pretty sure you all have this one, right? So that's one way that you can represent it. Or you can also think about different ways. So let's do the same thing. Yeah. We can also have tree diagram for that. So that's one way. table, and we have still same ball, and you can think about tree diagram. So let's think about the first row, and then second row. Okay, so first row, what could be the colors that I can have for the first row? It can be red, it can be white, or it can be green, right? So that's the first row. We can use the branches. Then we replace them, we flip back. So for second row, what can I have? I can still have red, white, or green when I had red for the first row, right? For my white color ball for the first row, I still can have red, white, green for my second row. Same for green ball for the first row. I can still have red, white, and green for my second row, right? Still, we can see that, oh, it's RR. This is RW. And this is RG. This is WR. We know how to interpret that too. Right? So when we see these letters, we can see, oh, that means first row is white, second row is green. This means first row is green, second row is red. So these are all possible outcomes, right? So this is more popular, way, I don't know if I can say popular, but more commonly used representation for the probabilities, okay, using tree diagram. Now let's consider the probabilities for each. So what's the probability to get red for the first draw? 1/3. Why? Because there's only one ball, one red ball, right? One red ball. What's the total outcome? RWG, 3. Right? So for to get red ball for my first row is 1/3. How about to get white ball? It's also 1/3. And also 1/3. Right? Now we replace the ball. So let's think about the second row. In a box, we still have those 3 balls, right? Each different color. So what's the probability for getting red color out of these 3 balls? What do you think, guys? Does this affect, does the first row affect the second row? So if I get red for my first row, does it impact whether I get red, white, or green for the second row? It doesn't. It doesn't. We still have 3 balls there. And the probability for red ball is still 1 out of 3, right? It's not affected. They're independent. 1/3 and 1/3, 1/3, 1/3, 1/3, 1/3, 1/3, 1/3, 1/3. Right? Then let's consider what's the probability to get red and red? Red and red. I just briefly said these 2 events are independent. They don't affect each other. My first row doesn't affect my second row because I put it back. It's still the same condition, right? So for this case, we can see, oh, it's 1/3 times 1/3. So the probability to get red and red is 1/9. Probability to get RW, red and white, 1/3 times 1/3 is 1/9. All of these are 1/9 because 1/3 times 1/3, 1/3 times 1/3, and so on and so on, right? So I can see that all of these are 1/9. 1/9, 1/9, and 1/9. Any question for that? No. Okay. So we see that these are all sample spaces for this event. Doing yours twice by replacing them, right? What's the probability for the whole events? So, the sample space. What's the probability for the sample space? Which means it can be red, 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 white, red, green, white, red, WWWG, all the way to GG. What's the probability for sample space? It should be 1. Remember? Probability for sample space is 1. So let's check if we get 1 for that. So 1 ninth plus 1 ninth plus 1 ninth plus 1 ninth. How many ones do I have? 9 of them. 1, 2, 3, 4, 5, 6, 7, 8, 9. So yes, if we add all of this together, it's gonna be 9, which is 1. So that's how you check, okay? So for any outcome you have and you find the probability for there, and when you add them together, it should be the sample space, the probability has to be 1. If it's not 1, if the sum of all the possible outcomes probability is not 1, something went wrong. You need to check, okay? So that's the key. Okay, now let's look at the problem here. What is the probability of obtaining GR? So green first, then red. We are talking about this event, right? We already found the probability for that, which is 1/9. Yeah. Right? How about obtaining either GR or RG? Now, next one is probability of either GR or RG, which means first row can be green, second row can be red, or the other way around. So this is OR situation, that's same as probability of GR or union RG. Remember when we talked about union or independent event? You can just do probability of green red and probability of red green. You can just add them together because there's nothing overlapping in the Venn diagram, right? So subtract from 0. So probability of green and red is 1/9. Red green is also 1/9. 1/9 plus 1/9. This is 2/9. Okay? So OR statement, you can add them together. OR statement, you can add them together. Okay? And like the first one, this is GR. So probability of GR, we can also think about this as probability of green and red. The first row is green and the second row is red. So we can also think about probability of green for the first one. I will just put 1 for the first row and 2 for the second row. The probability of green for the first row and you're multiplying that. Red for the second row. 1/9 times 1/9. I mean 1/3 times 1/3. Right? Getting green in the first row is 1/3, and getting red in the second row is 1/3. So we have 1/3 and 1/3, which is 1/9. Okay, so remember, if you have independent event, if it says and, you can multiply them. If it says or, you can add them. Okay? Now let's look at the third one. Obtaining R on the second row. R on the second row. So let me use my green color. Okay, red. R on the second row. So I see R here. I see R here. I see R here. In the second row. Right? Which is these cases. This one, and this one. So the first row doesn't matter. First row can be red, first row can be white, first row can be green. The second row has to be red. That's what it means, right? So we are looking at these cases, these 3 events. It says obtaining R on the second row. So are these and or situation? My question is, do you need to multiply 19 by 19 by 19, or you need to add 19 by 19 by 19? And it's all situation. It can be, because we are drawing twice, right? So we can have RR, or we can have WR, or we can have GR. So for this case, you need to add them together. So 19 plus 19 plus 19 is 39. 39, you can simplify that as 1/3. I divide them both by 3. So not bad, right? Okay. Any question? No? Anything to show here? Here's another situation. A box, there's another box that contains one black ball and two white balls. A little bit different now, right? Previously we had all three different colors. Now, two balls have the same color, only one ball is different color. How about you struggle with this one first? If a ball is thrown at random and a color is recorded, okay, we are drawing only one ball. So how will that tree diagram look like? You make it? Make a tree diagram. So what are the possible colors? Black or white, right? You can have black or white. It's the only cases, right? Now let's consider the probability to get black ball out of blue balls. What is it? How many black balls are there? Just one. Out of how many balls? 3. It's gonna be 1/3. How about getting white balls? Just white ball. There are 2 white balls, right? So it's gonna be 2/3. When you add them together, you have 3/3. 1. So yeah, that makes sense. Okay. So we can have that. Then the ball is replaced. Now let's think about the second draw. Okay. So let's continue. Now this is the first draw. And we have second draw. The ball is replaced, so it's back there. So let's think about second draw. What colors can I have for the second draw? I still black and white, right? I still have black and white. For the second draw, I still can have black and white because I flip back, right? Then what is the probability to get the black ball for the second draw? It's the same thing because I replaced it, right? It's gonna be 1/3. And white ball, I still have 2 balls, 2 white balls out of 3 balls, so 2/3. Same here, 1 black ball out of 3 balls, 2 white balls out of 3 balls. Are we good? Then let's look at the outcomes. So my outcomes are EB, which means first black, second black. E white, first black, second white. White B, then WB, white and black. WW, first white, second white. Very good, right? What are the probability for each of these? Morgan, what do you think about the first one? Probability of BB. 1/4. How did you get 1/4?
Oh, I guess there's only 3 because 2 of them are the same.
So we are looking at first ball is drawn as black and second ball is drawn as black. So black and black. What's the probability for that? Yeah. It's gonna be 1/9 because it's black and black, and they are independent. So yes, it's good. How about black and white? Shona? Where did you get that? You looked at only white here in the second row. You need to look at the first row and second row. The first row is black, which is 1/3, and second row is white, which is 2/3. And it should be 2/9 then, right? 1 times 2, 3 times 3. Okay? Okay, so is it? Probability of white and black.
It would be
2/9 as well, because we have 2/3 for white, right? 2/3 times e 1/3. It is 2/9. Okay? Elisa? Why? 4/9. Because the first white is 2/3, and second row is also 2/3 because it's replacing. And we have 4/9. When we add all of these probabilities together, what do we get? 1 plus 2 plus 2 plus 4, 9. 9/9, 1. So yes, it works. Okay? Any question for this? Okay, I think you guys are good at this. Okay, so let's continue with this. Okay, so we already talked about that. Now we are having another event here. This time we are rolling a pair of dice. Pair of dice means you have 2 dice, right? You have 2 dice. And you're gonna find the sum. So how would you do that? You can either use table, like the first example that we had, right? Or you can use the tree diagram. Whichever you like to do, please represent this event, rolling a pair of dice. And those who are online, you guys need to show me your notebook when you're done, okay? So show me all the sample space for a pair of dice and then sum. How many of you are using table? How many of you are using tree diagram? Look around to see what you're doing. What are you going to do here? We need to find the sum, right? So yeah, you can continue to nothing else. So this is 1 more in the second one. We can find 1, 2, 3, 4, 6. And 1 need to be a sum. So what is the sum? Or before the sum, I just pair them up. You can place a 1 over pair. And what you need to do is sum because you have to. Yeah.
You don't like
I actually like this one for this question because we have too many branches there. But this works too. And then you need to find the sum. You can use one, two, three, and then find the sum instead. Or you just find the sum and keep going. Okay, that's also good. Okay, you guys do well. How are you guys doing on the Zoom? Okay. Let's make sure. Okay, so take a look at mine. I use the paper here. We have two dice, right? A pair of dice. So I have one here and the other one here. Then sample space can be 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, and so on and so on. So I'm pretty sure you guys all have this one, right? Either it is a tree diagram or it is a table. You have all these outcomes. But we are more concerned about finding the sum. So for this one, what's the sum for this? What's the sum? 2, 3, 4. We are adding these two numbers together, right? So first row is 1, second row is 3. What is the sum? 4. So for this one, sum is 5, sum is 6, 7, and so on and so on and so on and so on. So if you find the sum, it's gonna look like this, right? So each table, you can change this to the sum, or you can make, you can, in the parentheses, you can find the sums like this. So we see the sum is from 2 to 12, 2 to 12. And some of the numbers are repeating, like 3, 3, 4, 4, 4, 5, 5, 5, 6, 6, 6, 6. Oh, I see the pattern there. But anyways, there are some repeating there, right? So if I ask you a question like, what's the probability of getting 12 as a sum when you roll 2 dice? What is the probability for that? Getting 12 as a sum when you roll 2 dice. What's the probability for that?
136.
136, because there's only one of the case, right? 12 is only appearing one as the sum. And how many outcomes are there in total? 36. So 136. What if I ask you the question like, what is the probability to get the sum of 6? Sum of 6. Let's look at the 6 as the sum. I have 1, 2, 3, 4, 5. Right? 5 outcomes out of 36 is going to be 536. Okay? I can also ask you, when can I have 6 as the sum? Then you can see all of these. So 1, 5, and I have my first row as 1, second row 5, or 2, 4, 3, 3, 4, 2, 4, 5, 1. Right? So we can interpret this table in any ways. Okay, so we got the sample space, and then we can apply, all the probabilities. So probability to get 2 as the sum, there's only 1 out of 36. To get 3, 2 out of 36. To get 4, 3 out of 36. To get 5, 4 out of 36. This is misspelled, 4 out of 36. To get 6, 5 out of 36. To get 7, 6 out of 36. To get 8, 5 out of 36. 36. To get 9, 4 out of 36. To get 10, 3 out of 36. To get 11, 2 out of 36. To get 12, 1 out of 36. Right? Then let me ask you one more question using this table. What is the probability to get the sum less than 4? The sum less than 4. What's the probability for that? Jalen? Sum less than 4. So sum should be less than 4 means sum is either 2 or 3. It's or, right? It can be 2 or it can be 3. So what do we do with these two probabilities? We add them. Very good. So it's going to be 336. Very good, very good. We can simplify that. Does it make sense? Okay, if I ask you a question with the same situation here, with this, okay. First row is even number and second row is also even number. Okay, I said first row is even and second row is also even. How would you find that? What's your strategy? I'm going to circle all of those cases. So 2 and 2 here, right? 2 and 4, 26, 2, 4, 4, 4, 4, 6, 6, 2, 6, 4, 6, 6. Those are the outcomes for even numbers, right? And then I'm going to see how many times I have. What is it? This is not regarded as a sum, but I have 1, 2, 3, 4, 5, 6, 7, 8, 9 out of 36. So that's when I have both first and second row even numbers. Okay? So we can use the same situation and find so many different questions for that. And you need to understand what the questions are. Okay? Okay, so let's talk about independent events more precisely. I already talked about independent events, right? So independent events are when the occurrence of one event has no influence on the other outcome of the second event. It doesn't affect the second event. Just like you are throwing a ball or you're throwing it back, then it doesn't, affect the second draw. So let's look at this example. You're flipping 2 coins. The event E1 is obtaining a head on the first coin. Okay, E1 is getting head on the first coin. That's why we put 1 because it's the first coin. Event E2 is obtaining tail on the second coin. Okay, E2 is the event obtaining a tail on the second coin. So let's consider you have 2 coins. Getting tail or head on the first coin, does it affect the second? No, it doesn't, right? It's not affecting each other, so they are independent events, right? So the outcomes should be head tail, head, or tail. This is all part of the outcomes. That's our sample space. What is the probability of getting head? It's 1 time out of 4. It's 1/4. Getting tail, 1/4. Getting 1 head and 1 tail. Well, this is 1 head and 1 tail, and that's also 1 head and 1 tail, right? It's gonna be 1/4 plus 1/4. Are you following me? Okay, so it's gonna be 1/2. Now I want you to consider this. 2 boxes. We have 2 boxes. In box 1, we have 2 white balls and 2 black balls. In box 2, we have 2 white balls and 3 black balls. Let B1 be the event of drawing a black ball from box 1, and B2 is drawing black ball from box 2. You understand what B and B2 is? B1 is getting black ball from box 1. B2 is getting black ball from box 2. Okay? Now, suppose a ball is drawn from each box, and we are interested in the probability that each ball is black. That is, probability of B1, box 1 is black, and box 2 is also black. Well, we already know that getting black from box 1 does not affect getting black in box 2. So they are independent events, right? They are independent. And it's AND, so we can just multiply them together. So we need to find out what's probability to get black in box 1 and probability to get black ball from box 2. Once you find them, you can just multiply them, right? Because it's AND intersection. Okay, so what's the probability to get black ball in box 1? Anna? 1 half, 2/4 or 1 half, right? Very good. How about in black ball from box 2? 3/5. So what's the intersection of that? We can just multiply them together, right? Yeah. So what is it? 1 half times 3/4. 3? 10? 1 times 3 is 3. 2 times 5 is 10. So yeah, it is 3 tenths. Okay. Now let's consider without replacement. So if once you draw the ball out, then it's out. You're not gonna put it back. Okay? Then do you think that's gonna be independent event? No, it's not. Why? Because it affects, right? Exactly. So this is not anymore independent event. Okay? So let's consider this. Suppose two balls are drawn one by one without replacement. Okay? So can you make a tree diagram and find the probability of outcome for that? You are drawing two balls. The first ball is not replaced. You need to think a little bit harder for this one. The second draw is affected by the first draw. So how about we do that together? First draw and second draw. Let me use the tree diagram again. So first draw, we have two different colors of balls, right? So black or red and white. What's the probability to get black from this one? 1/3. To get white? 2/3. So when you add them together, it's 3/3. Okay, good. Now, are we replacing that ball or not? We're not. No. So once you take out black ball, there's no more black. So to get black ball, it's 0. It's 0, right? It's impossible to get black once it is drawn from the first draw. How about to get white ball? How many balls are left once your black ball is out? So just 2 are left, and how many are white? 2 are white. So 2/2. Do you agree? Yeah. And do you see how the denominator is changing this time? You see that? Because in the first row we had 3 balls, but in the second row that ball is out. There are only 2 balls left. So when you are not replacing the ball, the denominators are changing. Okay? So you need to pay attention to that. And now let's suppose we drew white ball for the first row. So one of the white is out because we're not replacing it, right? What's the probability to get black on the second row? So this one is gone. 1 half, because there are 2 balls left and one is black and one is white. So to get white is also 1 half. Okay? So whenever you see the each branch is here from the same root, you can add them together and you need to get 1. You see that? 0 plus 2/2 is 1. 1 half plus 1 half is 1. 1/3 plus 2/3 is 1. Okay? All right? So now let's look at all the outcomes from first to second. So first and second together we can put BB, which means first board is black, second board is black. First board is black, second board is white. First board is white, second board black. First white, second white. Let's use our common sense for now before we calculate anything. You drew first board black out, and second board can be black. No, there is no more black. So automatically we can think, oh, that's not possible. It's impossible. It will be 0. We can also calculate that. 1/3 times 0 is 0, right? So probability to get black and black is 0. Okay, so I strongly encourage you to use your number sense to check. We can also write this from 1/3 times 0. Okay, how about getting black and white? So black is the first ball, white is the second ball. Okay, what's the probability for that? 1/3 times 10 over 2, which is 1. 1/3 times 1 is 1/3, right? Okay, so we go 1/3 times 2. Okay, 1/3. What's probability to get white first and black next? 1/3. How did you get that? 2/3 times 1/2, right? 2/3 times 1/2. You can see this will be cancelled, and I have 1/3. Good. Last one. Without calculating, it has to be what? 1/3, because the sum has to be 1. So let's check if it is 1/3. We have 2/3 times 1/2. 2/3 times 1/2. It's again cancelled. And we have 1/3. Yes, 1/3. And of course, the probability sum of all the probability is 1. So yes, we check several ways. Right? Okay. I think you guys are good. Yeah, so when you're not replacing it, you need to pay attention to the denominator. Okay. I have a few more examples for you guys. I think this is getting fun. What do you think? Yeah, do you agree? I think this is really fun. I love problems like this. Here is a shoebox, and I put 11 letters: PROBABILITY. Okay. Some letters are repeated, like B. I see B here and there. What else? I. And 2 I's. Anything else? I think that's it, right? Okay, anyways, there are some letters repeated or some letters just write it down. Suppose 4 letters are drawn at random. You are taking 4 letters out and you want to make without replacement. Once it's out, it's out. Okay, you are not replacing it. Keep it in mind. What is the probability of the event consisting of the outcome? Baby. So let's do this together, and then I'm gonna give you a fun activity to do. Okay, so let's consider making BABY. So the first row has to be B, right? What's the probability to get B for the first row? Total, there are 11, so I know the denominator will be 11. How many B's are there? 2. So to have the first B is 11. Okay, that's easy. Okay, so we are done. So we use, let me rewrite it. So let's suppose we took out this one. And how many are left now? How many letters? How many letters total? 10. So next one, the denominator will be 10. Right? Whatever it is. Okay, now let's see. A. How many A's do I have? Just 1. So 1/10. Right? Now is gone. So what is the denominator for the next probability? 9, one less, right? And how many B's do I have? Just one. And now what's the denominator? That B is also gone. I have now 8 letters left. What's the probability to get Y? Just 1. So this will be the probability for this event to get BABY without replacement. Can we simplify this? So whatever that is, it's gonna be 1 over something. 11 times 9 times 4. One over 960. Looks like. Okay, now I want you to think about integrating this with English. So maybe some of you have played scrambling words problem, something like that. So you're gonna scramble these words, these letters, and make them a word. What are the possible words that you can make out of these letters? Like Bob, related to the baby. Bar, B-A-R? So, what else? R-O-B. Anything else? Ability. Ability. Anything else? Pro. So you have so many. I think I'm pretty sure we have more. Like, I don't know. Anyway, we have more than this, right? So think about all of these possible, words that you can make. Just choose one and think about the probability for that. So choose one word, okay, and find the probability and let me know which word do you choose. Morgan, are you gonna the ability?
No.
It takes too much time. Okay, find something. Okay, find the word. You can make your own word, or you can choose one of these. Okay, but I really want you to find the probability for that. Shirley, which word are you doing? Bob? Bar. This one. Okay. Ebony, which one are you doing? Pro. Okay. How about you, Jalen?
Really the same one as Ada.
What is it? Same as
Bar.
bar. Okay. How many? Is there anybody else who's doing different thing? Different word?
I'm doing Bob.
Bob. Okay, Bob.
I'm doing Bar.
Bar. Bob or bar. You're playing Bob or bar. You're done, Teresa?
Yep.
Okay. What did you do?
I did pro.
Pro. What did you get for that probability?
1 over 990.
1 over 990? 990? Who did a pro? Who else did a pro? Ebony, did you get the same answer?
Yeah.
Okay. So can you tell me how you did it? The probability to get P, what is it?
1 over 11.
1 over 11. And we have now 10 letters. And R, how many R's do we have? Only one?
Yeah.
Okay. And O? Only
1 again.
Yeah, 9. Okay, very good. But this was easy because you have only 1 letter of that. Is there anything with anybody with Bob? Okay, who did a Bob? Okay, probability to get Bob. What is it?
2 over 11. Oh, do you just want the end answer?
No. How you got it? So For B first B, you got 2/11
Times 110.
110. Because we have 1, okay? 190. Excellent.
It's 1/490.
1 over
495.
495. Okay, so I think it's gonna be a fun game for you to do with your students if you have anything like that. Okay, great job. Are we done?
Yeah.
How about this section? No, we are not done. So this homework is not due until Friday, okay? Don't worry about that. Oh, not due. It's gonna be on Monday. I think it says Monday. But I could be wrong. Okay, anyway, it's not due Friday, so don't worry about it, okay? Alright guys, great job. I will see you guys on Friday.